A number of different Markov models of DNA sequence evolution have been proposed. These substitution models differ in terms of the parameters used to describe the rates at which one nucleotide replaces another during evolution. These models are frequently used in molecular phylogenetic analyses. In particular, they are used during the calculation of likelihood of a tree, and they are used to estimate the evolutionary distance between sequences from the observed differences between the sequences. Introduction. These models are phenomenological descriptions of the evolution of DNA as a string of 4 discrete states. These Markov models do not explicitly depict the mechanism of mutation nor the action of natural selection. Rather, they describe the relative rates of different changes. For example, mutational biases and purifying selection favoring conservative changes are probably both responsible for the relatively high rate of transitions, compared to transversions in evolving sequences. However, the Kimura model described below merely attempts to capture the effect of both forces in a parameter that reflects the relative rate of transitions to transversions. Evolutionary analyses of sequences are conducted on a wide variety of time scales. Thus, it is convenient to express these models in terms of the instantaneous rates of change between different states. If we are given a starting state at one position, the model's Q matrix and a branch length expressing the expected number of changes to have occurred since the ancestor, then we can derive the probability of the descendant sequence having each of the 4 states. The mathematical details of this transformation from rate matrix to probability matrix are described in the Mathematics of Substitution Models section of the Substitution Model page. By expressing models in terms of the instantaneous rates of change, we can avoid estimating a large numbers of parameters for each branch on the phylogenetic tree. The models described on this page describe the evolution of a single site within a set of sequences. They are often used for analyzing the evolution of an entire locus by making the simplifying assumption that different sites evolve independently and are identically distributed. This assumption may be justifiable if the sites can be assumed to be evolving neutrally. If the primary effect of natural selection on the evolution of the sequences is to constrain some sites, then models of among-site rate heterogeneity can be used. This approach allows one to estimate only one matrix of relative rates of substitution, and another set of parameters describing the variance in the total rate of substitution across sites. DNA evolution as a continuous time Markov chain. Continuous time Markov chains. Continuous time Markov chains have the usual transition matrices which are, in addition, parameterized by time. Specifically, if are the states, then the transition matrix where each individual entry refers to the probability that state will change to state in time. Example: we would like to model the substitution process in DNA sequences in a continuous time fashion. The corresponding transition matrices will look like, where the top left and bottom right 2 times 2 blocks correspond to transition probabilities and the top right and bottom left 2 times 2 blocks corresponds to transversion probabilities. Assumption: if at some time the Markov chain is in state, then the probability that at time it will be in state depends only upon, and this then allows us to write that probability as. Theorem: continuous time transition matrices satisfy. Note: there is here a possible confusion between 2 meanings of the word transition. In the context of Markov chains, transition is the general term that refers to the change between 2 states. In the context of nucleotide changes in DNA sequences, transition is a specific term that refers to the exchange between either the 2 purines or the 2 pyrimidines. By contrast, an exchange between one purine and one pyrimidine is called a transversion. Deriving the dynamics of substitution, consider a DNA sequence of fixed length M evolving in time by base replacement. Assume that the processes followed by the M sites are Markovian independent, identically distributed and constant in time. For a fixed site, let be the column vector of probabilities of states and at time, let be the state space. For two distinct, let be the transition rate from state to state. Similarly, for any, let the changes in the probability distribution for small increments of time are given by, in other words, the frequency of S at time is equal to the frequency at time minus the frequency of the lost S plus the frequency of the newly created S. Similarly for the probabilities, we can write these compactly as where, or, alternately, where, is the rate matrix. Note that by definition, the columns have sum to 0. For a stationary process, where does not depend upon time t, this differential equation is solvable using matrix exponentiation and ergodicity if all the transition probabilities are positive, i.e., if all states communicate. Then the Markov chain has a unique stationary distribution where each is the proportion of time spent in state after the Markov chain has run for infinite time. Such a Markov chain is called ergodic. In DNA evolution, under the assumption of a common process for each site, the stationary frequencies correspond to equilibrium base compositions. When the current distribution is the stationary distribution, then it follows that using the differential equation above, time reversibility definition, a stationary Markov process is time reversible if the amount of change from state to is equal to the amount of change from to. This means that not all stationary processes are reversible. However, almost all DNA evolution models assume time reversibility, which is considered to be a reasonable assumption. Under the time reversibility assumption, then it is easy to see that definition the symmetric term is called the exchangeability between states and, in other words, is the fraction of the frequency of state that is the result of transitions from state to state. Corollary: the 12 off-diagonal entries of the rate matrix can be completely determined by 9 numbers. These are 6 exchangeability terms and 3 stationary frequencies. Scaling of branch lengths by comparing extant sequences. One can determine the amount of sequence divergence. This raw measurement of divergence provides information about the number of changes that have occurred along the path separating the sequences. The simple count of differences between sequences will often underestimate the number of substitution because of multiple hits. Trying to estimate the exact number of changes that have occurred is difficult, and usually not necessary. Instead, branch lengths in phylogenetic analyses are usually expressed in the expected number of changes per site. The path length is the product of the duration of the path in time and the mean rate of substitutions. While their product can be estimated, the rate and time are not identifiable from sequence divergence. The descriptions of rate matrices on this page accurately reflect the relative magnitude of different substitutions. But these rate matrices are not scaled such that a branch length of 1 yields 1 expected change. This scaling can be accomplished by multiplying every element of the matrix by the same factor, or simply by scaling the branch lengths. If we use the beta to denote the scaling factor, and nu to denote the branch length measured in the expected number of substitutions per site, then beta nu is used the transition probability formulae below, in place of mu t. Note that nu is a parameter to be estimated from data, and is referred to as the branch length, while beta is simply a number that can be calculated from the rate matrix. The value of beta can be found by forcing the expected rate of flux of states to 1. The diagonal entries of the rate matrix represent -1 times the rate of leaving each state. For time-reversible models, we know the equilibrium state frequencies. Thus we can find the expected rate of change by calculating the sum of flux out of each state weighted by the proportion of sites that are expected to be in that class. Setting beta to be the reciprocal of this sum will guarantee that scaled process has an expected flux of 1. For example, in the Jukes Cantor, the scaling factor would be 4, because the rate of leaving each state is 3 mu, 4. Most common models of DNA evolution. JC69 model. JC69 is the simplest substitution model. There are several assumptions. It assumes equal base frequencies and equal mutation rates. The only parameter of this model is therefore the overall substitution rate. As previously mentioned, this variable becomes a constant when we normalize the mean rate to 1. When branch length is measured in the expected number of changes per site, then it is worth noticing that what stands for sum of any column of matrix multiplied by time, and thus means expected number of substitutions in time for each particular site when the rate of substitution equals. Given the proportion of sites that differ between the two sequences, the Jukes Cantor estimate of the evolutionary distance between two sequences is given by the and this formula is frequently referred to as the distance. It is a sufficient statistic for calculating the Jukes Cantor distance correction, but is not sufficient for the calculation of the evolutionary distance under the more complex models that follow. K80 model. The K80 model distinguishes between transitions and transversions. In Kimura's original description of the model, the alpha and beta were used to denote the rates of these types of substitutions. But it is now more common to set the rate of transversions to 1 and use kappa to denote the transition-transversion rate ratio. The K80 model assumes that all of the bases are equally frequent. Rate matrix. The Kimura two-parameter distance is given by, where P is the proportion of sites that show transitional differences and Q is the proportion of sites that show transversional differences. F81 model. Felsenstein's 1981 model is an extension of the JC69 model in which base frequencies are allowed to vary from 0.25. The HKY85 model can be thought of as combining the extensions made in the Kimura 80 and Felsenstein 81 models. Namely, it distinguishes between the rate of transitions and transversions, and it allows unequal base frequencies model in 1984 using a different parameterization. That latter model is referred to as the F84 model. Rate matrix. If we express the branch length nu in terms of the expected number of changes per site, then and formula for the other combinations of states can be obtained by substituting in the appropriate base frequencies. T92 model. T92 is a simple mathematical method developed to estimate the number of nucleotide substitutions per site between two DNA sequences. By extending Kimura's two-parameter method to the case where a G plus C content bias exists, this method will be useful when there are strong transition, transversion and G plus C content biases, as in the case of Drosophila mitochondrial DNA. 1. Frequency-only rate matrix. The evolutionary distance between two non-coding sequences according to this model is given by where is the GC content. T92 model. The T92 model distinguishes between the two different types of transition, i.e., is allowed to have a different rate to. Transversions are all assumed to occur at the same rate, but that rate is allowed to be different from both of the rates for transitions. T93 also allows unequal base frequencies. GTR is the most general, neutral, independent, finite sites, time-reversible model possible. It was first described in a general form by Simon Tavare in 1986. The GTR parameters consist of an equilibrium base frequency vector, giving the frequency at which each base occurs at each site, and the rate matrix where are the transition rate parameters. Therefore, GTR requires 6 substitution rate parameters, as well as 4 equilibrium base frequency parameters. However, this is usually eliminated down to 9 parameters plus the overall number of substitutions per unit time. When measuring time in substitutions, only 8 free parameters remain. In general, to compute the number of parameters, one must count the number of entries above the diagonal in the matrix, i.e., for n trait values per site, and then add n for the equilibrium base frequencies, and subtract 1 because is fixed. One gets, for example, for an amino acid sequence, one would find there are 209 parameters. However, when studying coding regions of the genome, it is more common to work with the codon substitution model. There are codons, but the rates for transitions between codons which differ by more than one base is assumed to be 0. Hence, there are parameters